1.
All right, now we're doing the first problem on homework 5. This first problem is to walk through Dijkstra's algorithm for this particular weighted directed graph. Now, what we have to do is check to see what the situation is at every step. After 0 steps, which means at the beginning, the only node that's on the queue, what we use is an updatable min queue. Actually, an updatable min heap. It's a priority queue, but it's an updatable min heap. And the only element on there is the only partially processed node, which is the source, which is A. All right, now, in the first step, we pop off A and give it the value 0. I'm representing that as a blue number here. Maybe I should use green instead, but I'm using blue. And we then push on all of the out neighbors of A, which are B, E, and F. And these values, these have weights, cost B 1, and E is 4, and F is 8. But that's indicated here by the fact that I have the 1 here for B, the 4 for E, and the 8 for F. The red numbers represent values on the min heap itself. Now, the number turns blue when we pop it off, which means we pop this off and got a 0. All right, now the next step is that B is popped off. And so we get a blue 1 there because it keeps that value. And we push all the children. Well, some of the children, one of the children is already there. So we have C, which has a value of 3 because it's, oh wait, this is a 1. And the C has value of 3 because it's 1 plus 2. And then we have, after C we have G, which is 1 plus 6, which is 7, and F, which is also 1 plus, F is updated. It was 8, but it's now 7, because we updated it, because we have a new value here. So this value is 7 for F, and 7 for G, and 3 for C. Now D has the value, it doesn't have a value yet. All right, now, we're now at this step here, after 2 steps. Then the next thing we do is delete the smallest one. Now that smallest value is C. It's not, if this thing is, min heap is being reorganized so that this will actually be in the position of the minimum. So we're not showing that structure here. And once we have C, then we can push on the elements which are, that C can reach, and that would be D, which has a value of 4. Now E is also an out neighbor. D is D. The out neighbors are, hold on. Wait, we have D, which is 4. Yes. And then we also have G, and 3 plus 2 is 5. So that means that this 7 is changed to 5, as we show here. All right, we have now completed that step. Our min heap now contains the elements E, F, G, and D, indicated by these red numbers, 4, 4, 7, and 5. Now, I'm changing this to black after it's been taken off once. It's not, we don't need to look at it anymore, and so we change that number to black. So 3 is the final value for C. All right, now, looking at the next one, we take the smallest one here. Now, the smallest one could either be E or D, but for whatever reason, I chose that we would do E first. And so now once we have E, we look at the neighbors of E. E is now off, let's see, that was a 4. And we update the values for the out neighbors. E has only one out neighbor, F, and since E had the value 4, the updated value here is 9. Now 9 is not less than 7. Therefore, the value of F is not changed. All right, now we're done with that. We give E the value 4, it's its permanent value, and then the next one we do was a tie. We could have done either one first. We do D next. Now, D is then popped off, and then we look at its out neighbors, H and G. Now this value here is a 1, which I forgot, and then if I take this, which is a 4, 4 plus 1 is 5, which beats 7. But it, no, but it was already a 5, wasn't it? So it doesn't change. All right, another out neighbor is H, and H acquires the value of 8. 4 plus 8, 4 plus 4 is 8. By the way, G now has changed to 5. And so I get an 8 here for H. Now, where is that shown? H, D is 4, H is, it should be here. This was missed. Okay, so I should have an 8 at this point. Okay, I'll have to check my output here. And actually, the text here, the picture is correct. It's just that I copied it incorrectly there. So far, the answer I gave is correct so far. All right, now, the next thing we pop off is G, and that's a 5, so that's its permanent value. And then, because G, out neighbor is H, we update this 8 to a 6. Now, we now have two, let's see, F is 6. How did that happen? When we did G here, we also update the value of F to also be 6. Because we had 5 plus 1 is 6, and so it improves that. All right, now at this point, we have 2 6s in the min queue, of the min heap. We pick either one of them. I'll pick G first. And, no, I will pick F first. But F has no out neighbor, so there's nothing to do. So we're done with that. Then we pick H. H has no out neighbors, so it's nothing to do. And now we're at the last step and we're finished. Now, I did not keep track of I did not show how I kept track of the back pointers here. But if I had done the back pointers, then it would become clear that all the back pointers would point to the correct places. For example, the back pointer of D would be C, and the back pointer of G is C, and the back pointer of C is B, the back pointer of A and B are both A. back pointer of H and F are both G. And from the back pointers then, going forward along the back pointers, I get the shortest path tree, and that ends that. Now we're going to work problem number 2 of homework 5 for 477, 677. Here we're supposed to use the Bellman-Ford algorithm to compute the single source minimum path tree for this directed weighted graph. Here where the start node is S and the other nodes are A through I. So we're going to keep the cost here. We have 2 arrays, cost and back pointer. All right, now we start with 0 for S and the back pointer is undefined. Now at every step we look at every edge, which is how different, that's why it's a quadratic time. Now, actually it's more than quadratic time because the number of edges could be n squared and we might have to go through n steps, so it could be as high as n cubed. But in reality it's really O of m times the length of the longest shortest path. Alright, now what we do now is starting from S we look at all the edges and we update the value. So these updated values will be obtained by following these edges. So we have, to A we now have a back pointer of S, to F we have a back pointer of, back pointer is S and the value is 7. For F the back pointer is S and the value is 5. And for E the value is 6 and the back pointer is S. Now theoretically we are looking at all the edges, but we don't get anything smaller than infinity for the other 6 edges yet, because we have not found any path to those edges. All right, now, when we update again, we're going to use more edges because we'll use these and also the ones coming out of E and the ones coming out of F. All right, so when we update this edge, we get 8 here. And we update this edge, we get 5, because 7 plus minus 2. And we update this edge, we get 4, which then modifies that. We get a better answer. This one is 9, 6 plus 3, and this one is 11, 7 plus 4. So the value at F is changed to 4, and its back pointer is changed to E. Now, we also get back pointers, new values in back pointers for other things here. Now you notice that when we did this thing, we had a 5 there, so we got an 8. But we're going to use that edge again to get a better value next time through. Let's see, G, we didn't get anything for G. For B, we got 9. And this gives you a back pointer of B. And what else did I get? For C, I got a 5 with a back pointer of A. And, wait, this B is 11 here, sorry. And the back pointer is A. I missed both. We haven't done G yet because we've only gone through 2 steps. But we did do H, and H has a value of 9 with a back pointer of E. And we still have not yet visited either G or I. All right, now we're going to go through all the edges again. First, checking to see if there's any update. Well, there's no update here, here, here. But here we get an update of 7. C to D, so that means that the value at D is changed to 7 and its back pointer is changed to C. Now, did we get any other changes? From 6, -2 is 4, no change here. And this value becomes 9 for G with a back pointer of B. And the value of H, the 1, that gives you a 10, but 9 is better, so we keep the 9. Now let's see if there are any other things that we need to change, and I think the answer is no. We went through, we didn't make many changes. But we did make some changes, which means we have to do it again. We stop when there are no changes. All right, now we'll check every edge here. 7, this is minus 2, 5. This works. This, no change there, no change there, no change there. Wait, we have a change. This becomes 8. So for I, we get a value of 8 with a back pointer of G. So since that's a change, we now have to iterate again through all the edges. They might think that's inefficient. And yes, it is, but that's how the algorithm runs. We then update this here. We have that already done. And this gives you a lower value here, which is 7. No. Which is 9. Oh, it's the same value. 6 plus 3 is 9, 8 plus 1 is 9. So there's no change. All right, now when we do this, we do that, we do this, we do that, we check these, we check all of these, and we see that no updates will occur. So that means that we now have the final picture. And using the back pointers, we can now fill in. The back pointer for A is S. The back pointer for B is A. The back pointer for C is A. The back pointer for D is C. No, the back pointer for D is C. The back pointer for E is S. The back pointer for F is E. The back pointer for G is B. The back pointer for H is E. And of course we could have picked the back pointer to be I. It's just as good, but we visited E first, and I did not displace E. So if we want to get the shortest path, we wouldn't go to H anyway, because that has more 1, 2, 3, 4, 5 edges, while this has only 2 edges, so it's preferable. The back pointer for I is G. And we're done. This red tree then is the shortest path tree, which is shown in color in red color in the printout of the answer sheet. Okay. All right, now we're doing the third problem on homework 5 of 477. Which is a loop invariant question. I've written the code in blue here. We have a function which returns, you enter n and it returns 2n. I called it double. Of course, we would actually never really use this. We would just write n plus n, or 2 times n. However, this is very simple-minded. It helps illustrate how loop invariants work. All right, now the loop invariant, as it turns out, is this equation that as you go through the program, 2p plus q equals 2n. And the loop invariant holds in 4 places, here, 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 and here. All right, now initially it holds because p is n and q is 0, so 2p plus q is simply 2n plus 0, which is 2n, so it has to hold. And it has to hold. If it holds here, it holds there. That's an implication. So if the old values, the values here are 2p plus q equals n, Then when I substitute the new values of p and q, which occur here, I have 2 times p plus p minus 1 and q plus 2, because I added 2 to q. Now when I work out what the loop invariant is, 2p minus 1 plus q plus 2, I discover that it's equal to the old values of p and q, 2p plus q, which is equal to n, which means the loop invariant still holds. All right, now looking at the end, we know that p is 0 because we exited the loop. And that means that the loop invariant here, 2p plus q is 2n. We know that 0 plus q equals 2n because the loop invariant holds. Because p is 0, so that means that q equals 2n, which is the output condition we need. Because we want to return 2n. And q is 2n, which means we actually now return 2n, which is what we're supposed to.